statistics which helps in quantifying the data. So certain assumptions or requirements here, we are talking about only variable. And when I say univariate data, we are talking about one variable. What is a variable? Variable is a characteristic which could be expressed in terms of numbers. So statistically, it is called as quantitative characteristic. So we are collecting data on this, and this data is now categorized into three cases. The first one is raw data, just the data collected in the unordered form. So there we indicate the data by the symbol X. Usually we use X, Y, Z to indicate the variables, and we collect certain data points on this variable x1, x2, etc., xn, and we say size of this data is n. So you are observing n data values in the unordered form. Now, when you feel that your n is large, you cannot deal with each and every point of that. In that case, we try to represent that in a discrete frequency distribution, provided the variable is discrete. So in that case, we'll have the values taken by the variable in the first column and frequencies in the second column. At certain times when you feel that n is still very large, the range is very large, or the variable is continuous, in that case, instead of writing all possible values of x, you represent that by small certain subranges called as class intervals, and such a distribution is called as continuous frequency distribution. So these are the three basic categories: raw data, discrete frequency data, and continuous frequency data. So when I say raw data, or you will have only the values of the variable given, no information regarding frequencies will be given, and the size of the data will be usually less. Like at the most you can have 15 or 20 data points, but usually it lies between 5 to 20. So in that case, you need not convert the distribution into frequency in order to obtain the measures. You will take those values of x as it is, and you will apply the suitable formula to compute the measures. When we have given you the frequency distribution, observe whether discrete points of x are given or the class interval subranges are given. Use the formulas which I specify for the case of discrete frequency distribution when certain distribution is given, and the formula changes for the measures when we talk about the continuous frequency distribution, but they summarize the same measure. We'll have different terms, different methods of estimating, but the definition remains the same, the terminology remains the same, and the method, though the formula is different, the method of accessing that measure remains the same. So we'll look into such three cases, three distributions. All are called as distribution. This is just raw data, raw distribution. These two are called as frequency distribution, discrete case as well as continuous case. So first we'll see why do we have to do the analysis for the collected data. So that is need for the analysis. So you could have certain questions. Write a note on need and various measures of analysis of univariate data. Now the first and foremost thing is data is unordered. So if you have the data unordered, it cannot help you in making any decision making. So you have to bring out the essence of data, what actually the data is telling. So you have to arrange it, and then you have to summarize it. So whenever you summarize the data, you can bring out the essence of the data. You can quantify the data using single numbers, which are easy to represent the entire mass of the data. And when you do the organization of the data, so drastically there will be reduction in volume, and reduction in volume helps us in drawing useful comparisons as well as decision making. So if you want to do some decision making based on the data, the first and foremost thing is you reduce the volume or you organize the data and try to bring out the essence of the data in terms of a single number. Because the reason is you cannot compare the multiple data points. You cannot compare multiple data points, or you cannot compare the raw data collected in the raw form. The reason is, say for example, even though you have the same set of values, say weights of say uh, first BSc students and say weights of second BSc students, almost the weight points will be same. But if you keep on comparing each and every value, at the most you can say, in the first case it is less, in the second case it is more, but the essence, where in which case, in which class the weight is uniform, where are we observing the maximum, minimum, what is happening to the weight in the lower 10% category, in the upper 10% category. So some objectives are there because of which I have collected the data. So if I want to make use of the data in a best form, then I need to do the analysis. Now here in case of univariate analysis, we try to obtain different measures based on the requirement, and those measures are broadly categorized into four particular groups. The first one is measures of central tendency. Then we have measures of position or location, and then measures of spread or dispersion, and then we have measures of skewness and kurtosis. So again, you can have a question, why do we need so many measures? As said, your objective as well as the type of the data, they vary from study to study, place to place, as well as from variable to variable. So based on the type of the data we have, based on the objective of the study, we will look into various possible measures. The reason why we have, another reason why we have these four categories is that at certain times we you know end up in getting the same measures. So our main objective is to decide, compare the data, select the data which is best for my study. So certain cases, what it can happen is that you may observe the same measures in two distributions. As I said, I have weight of first BSc, weight of second BSc. The average or the mean might come out to be the same number. So in that case, measure of central tendency is not helping in deciding which is the distribution, better distribution. So I should go and look into the other possible measures which judges the consistency or the uniformity of the distribution, and then I could select that particular data set in area of my research. So that's the reason why we have these certain cases. Now let us see these measures in detail. So I'll first talk about measures of central tendency. So let us understand what is the central tendency and what is the reason. I could say the reason for this particular property or behavior is somewhat natural. You can observe that in nature. So what behavior are we talking here? So you are extracting some data points. So let me say you are looking into the as said, the weights of the students recorded in kgs of a particular class. Then let me say I have 56, 48, 63, 62, 59, 50, 61, 49. So I'm just recording the integer part of the values. So if I record certain data, now you can see that most of the data points or almost all the data points can be observed to be closer to a particular value called as central value. So whatever may be the type of the variable, almost all the variables which exist in the nature, in most of the cases you can observe this behavior. For that matter, you can do a simple exercise. Try to collect some data points like say number of people living in a family for say 10 families of your locality, or say the ages of your classmates, the weights of your classmates. So keep some variable in mind, extract some data. You will observe that most of the values are closer towards a central value. So what we are observing is that there is certain property or behavior. What is that behavior? The behavior is concentration of values towards a central number. Concentration of values towards a number. We call that a central number because usually that happens to be the value in between the observed values. So this central number is called as average statistically, and in a layman language we call it as measure of central tendency. So we are observing the behavior that most of the data points are close to that number. That number is called as measure of central tendency, or statisticians call them as average, and the behavior or the property of observing the concentration of values towards a central number, that is called as central tendency. So they'll ask the definition of central tendency as well as the definition of average or measure of central tendency. Now the question is, why do we need the measures of central tendency? Are the positions or just the spread are sufficient? Why do we need them? I said the reason is each and every data point is giving you certain information, but it is giving you only a part of the characteristic of the population or the sample where the data point is extracted. Now you want to summarize this. That is, many such data points are there, many information are there. If you could bring out the essence of this information through a single number, then that number will be easy to remember. That number represents the entire data set. It can be easily used to compare two data distributions. Say, for example, if I have distribution 1, distribution 2, as said earlier, comparing and making, bring out the essence of the data while comparing each and every point is not, mathematical and not logical also. So what we try to do is, you represent this by a single number. If you have another distribution represented by a single number, now if you could compare that single number, you can say in which case the weight is more, in which case the weight is large, and such decision could be easily made. So decision making becomes easier when you have measures of central tendency. The reason is that that single number reduces the mass further, and it represents the entire mass, represents the entire mass or the entire data set. That is the reason why we need this. Now the question is, how do you come up with that number? So I said many numbers are closer to that particular number. So I can say here most of the numbers are closer to say 56 or 57. You could tell no, it is close to 58. I could observe three values which are close to 63. So why can't you say 60 as the middle number? So many such numbers exist, but if you apply your personal judgment, each of you could come up with a different answer for that certain central measure. And in that case, if you look into the definition that it is a central value where much of the values are concentrated, all your answers are logically correct. Now again, the problem exists. If each of you come up with your own single number, then again the same problem of decision making becomes difficult. So you have to somewhat generalize this central value using the mathematical concepts. So we apply certain techniques, certain definitions, and we come up with certain formulas or certain methods which helps us in identifying these central numbers. And those are broadly again categorized into 5 cases. So it would say measures of central tendency are of 5 cases. Again, the question, why do we need 5 cases? Is one number not sufficient? So I said the variable, the scenario, the objectives are different based on the different cases, different types of data. We look into different measures. And one of such measure which is most commonly used when it comes to the analysis of univariate data is arithmetic mean. Then we have median and mode. They are also used much widely, but less widely compared to arithmetic mean. Then we also have the special averages called as geometric mean and harmonic mean. So they are not that widely used compared to the above 3, mean, median, and mode. So this arithmetic mean, in the language of layman, it is just mean. So if you observe that any person who just has the basic knowledge of statistics or doesn't have the knowledge of statistics, if he says mean or average, he means he's talking about arithmetic mean, but statistically speaking, all these five measures are called as average. So if the question in your examination just says average, as said, will be, or the question is pointing out in the direction of arithmetic mean. If I specifically use, it says, the question says median or mode or geometric mean, then you have to talk about that particular average. So if you just see the word mean or average, then you have to just talk about arithmetic mean. Now let us understand each one of this and see what are the formulas and techniques available in order to compute them for various cases of the data. So arithmetic mean, so if we have the variable as said indicated by x, then we define the arithmetic mean, and it is abbreviated as AM and also indicated by x bar if you are using the variable x. If the variable used is y, then we can indicate it by y bar, z bar. If you're using x1, x2, x3, then you can have x1 bar, x2 bar, x3 bar, and so on. And this is defined as sum of the observations divided by number of observations. So what are all the data points you have, you use them and obtain the sum, divide the sum by the count or the number of observations, and we call that as the arithmetic mean. So what do we mean by this formula or this technique or this definition is that you have some variable, you are observing certain data points on the variable, or you are collecting certain data points. As said, we are observing n values, and statistically these values are called as observations because we are personally observing or recording by conducting some experiments or certain experiments or actions in order to extract the data. Therefore we coin the term observation to indicate each of these values. Now if you look into the definition, it is just the mathematical form of this. So you can say arithmetic mean is defined as the ratio of sum of observation to number of observations. So when I mean sum of the observations, so I mean the total of all the values considered as the data point. So you have x1, x2, etc., xn. You add all those values, you divide it by n. Now we come up with certain notations which help us in simplifying the formulas. So if every time writing the formula as x1 plus x2 etc. plus xn becomes difficult, so we have using certain shortcut notations to indicate the totals as well as the products. And you already know about this symbol sigma, which indicates the total. So we had used this to indicate the total frequency, capital N or sigma f. Now here I'm talking about the total of the values taken by our variable x. Therefore this x1 plus x2 plus xn now simply be indicated as sigma x, and we have n, and this is the formula to compute arithmetic mean when you have just the values of x available. So as said, if you just have the values of x, we statistically call that as raw data. So there is no need for you to arrange it or organize it or convert into frequency distribution. As said, whenever we are talking about raw data, we see that the sizes very less. So addition of the numbers or obtaining the sum becomes very easy since you'll be dealing with the calculators. So the arithmetic mean can be easily computed. Now extending the same concept of sum of the observations divided by number of observations to discrete frequency data and continuous frequency data, we can get a formula for arithmetic mean. ಬರ್ಕೊಳ್ಳಿ first formula arithmetic mean for raw data. raw ಅಂತ ಬರ್ಕೊಂಡು bracket ಅಲ್ಲಿ when only x values are given ಅಂತ ಬರ್ಕೊಳ್ಳಿ. Raw data when only x values are given, am is equal to x bar is equal to sigma x by n. You can write these two forms also, which acts as the definition of arithmetic mean. Done. Okay, so we'll take an example here. Let me use certain numbers. So I have 2, 4, 6, 7, 14, 17. Let me take some more. Okay, so I have n is equal to 7, 3, 21 minus. So 20 values are given to you, and you have to quantify this using the suitable average. Now, sometimes the question will say that study the data and use suitable average. While discussing most of the cases, I'll talk about the various scenarios where mean can be used, and please concentrate on the technique. So for all the data, you cannot use arithmetic mean. So arithmetic mean has its own disadvantage, and sometimes the data could be such that if you apply arithmetic mean and compute the value, that will be totally fails in representing the entire mass. So I'll show how it fails and how it works. So let us now first understand how to compute the arithmetic mean for raw data. Now, when you talk about the variables like say age, weight, height, marks of the students, number of thefts happening, number of defective items produced, number of accidents happening in a road per day. And for all such cases, when your n is certainly say large, you can always apply the concept of arithmetic mean in order to quantify the certain set of observations by a single number. So here, as said, you have been just given with the values of age, so which we call as raw data. So let us quantify it by a variable. So let x is equal to age in years. Then I have to obtain x bar. So here I say the suitable average is x bar, because for any continuous variable you talk about as a like height and weight, age, or the weight of newborn baby, number of defective items, marks scored by students in certain examination, all those things can be easily quantified by the concept of arithmetic mean, provided you don't have what called as an extreme value in the data. So ನಿಮ್ಮ ಡೇಟಾದಲ್ಲಿ extreme value, I could simply define it as that value which is not suitable for the given data. So it's somewhat like say odd one out in the data point. So if you could come across certain such numbers, then the mean cannot be computed. What happens is that the extreme values will have an influence in the value of arithmetic mean. So the computation of arithmetic mean is possible, but the generalization doesn't, come to be a good one. So here, most of my data values are like say age of the persons, say up to 30 or 40 years. So I could say that if you just look into this number, 37, other than 37, most of the values are below 30. So I could doubt that whether this is an extreme value. That 7 is a possible number for age, but if I say where have you collected this age, maybe say the age of say students doing their MTech and MSc, in most of the cases it is somewhere below this. So or the students who are studying in say certain university, so the ages are possible. So 37 is also a possible age. A student who is doing his last masters or research work, that is a possible value. But there are certain techniques of identifying and quantifying these extreme values, and you have to check back to verify this data point. Is it actually 37 or is it actually 27, which is mistakenly written as 37? Now for time being, so when you look into the questions in the examination, data given to you will be in most of the cases free from the extreme cases only, and in as said most of the cases will tell you what particular method has to be used. So let us assume that there are no extreme values in this case, and we'll compute the mean. This is raw data, so the formula to compute mean is total of observations divided by number of observations. Now compute the total. So I need not write it as 23 plus 21 plus 18. That is not required. You have the values, you have the calculator, add them and tell me the total. Hey, just want the total.
400.
400. In this count 20 is correct, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 17, 18, 19 ashtay. Okay. So I have only 19 values given to me. So the mean will be 400 divided by 19, which comes to 21.0526. And at certain cases, the precision and accuracy of the measure is important. So we usually stick to 4 digits after the decimal point. So it's left to you how many digits you use. But whenever you are using a certain measure, certain value in estimating or obtaining another measure, please maintain the accuracy. And if you are just, doing the decision just based on this particular measure and that is not being used further in the further algebraic analysis, then the number of digits you will record is left to your personal judgment. So we are telling that most of our data points are closer to 21.05. So if you practically look into that, you could say many values are say 23 or 25. So why did the average come to be 21? That is the behavior of arithmetic mean. So it treats every value equally. So you have a value data point 13 and 37. You have a data value say 25. Every value is considered. Every value is treated equally. So every value influences the average. So you have two data values which are extremely low. So these have dragged the average towards them. Now instead of 13, if you had 20 there, naturally the sum will increase and your average may turn up to 23 or 25. Now talking about the influence of extreme values on the mean. Now instead of say 25 as the last value, if you have recorded that as 250, then if you look into the value of arithmetic mean, so it will be 400 minus 25 plus 200. So the total comes to 575. And if you look into the value of mean, now that is 30.26. What happened to this value? It is violating the property that most of the values are closer to that. So I could have one or two data points, but when you look into much of the cases, all are say far away from this number. So only this number is closer to that, and these two necessarily are not closer. So why does mean suddenly got increased to 30.26 from 21? That is because of the presence of this number, odd one. So when you are certainly know that you are accepting the age for a certain set of students, then you can go back and check that, oh, it is not actually 250. We have recorded it wrongly as 250, but it is 25. Then do a background verification on the data and make sure that it is not extreme value and then compute. Now the question, you have done the background check, but the 250 is a value taken by some variable. Now the question is, do I have to include them in the data? Now, if I include that in the data, we just saw what is happening to the measure. So it is failing to represent the entire mass. So it's better I remove that extreme value. So even after checking it twice and thrice, if we feel that 250 is the correct value, but it is an odd one out for this group, then you just completely remove it from the group. Now the question, on what basis do you remove? So I said, whatever you do for the data, always use the mathematical and scientific methods. Otherwise, your personal judgment will truly alter the value of the average, And once your values are altered based on your personal judgment, we say the personal bias is involved in the computation, and that might not, whatever the results you observe may need not be true for the general population. So generalization becomes very difficult. Now the question, is there any scientific technique or mathematical technique available in identification of these extreme values and the removal of extreme values? Yes, we have. We'll look into those methods as we proceed in the class. The next type of distribution what we observe is discrete frequency distribution, where you will have discrete values of x and frequencies given, and there also we generally indicate that your variable is taking n data points x1, x2, xn with frequencies, respective frequencies f1, f2, fn, and then we say the arithmetic mean in that case is given by the formula total of f into x divided by total of f. So what are the computational steps? The steps are that you have been given with a column of x and f, you multiply every respective value of x with its respective value of f and obtain the values of fx and the total of f as well as total of fx, and then obtain the mean as the ratio of sum of fx to sum of f. Now, the sum of fx is the sum product of f into x. So it is not like your sigma f into x. It is not that. So it cancel out x other sigma fx indicates the total of the column f into x. So first you have to do f into x. Now the question, how is this equal to the same definition what we observed in the previous case? So we have the same set of x values. The only thing is that we are talking about the repetitions. So when we talk about repetitions, adding a certain number of x n number of times or f number of times is same as multiplying it by f times. So you have a particular number, say x1 repeated for 5 times, then for the sake of arithmetic mean, you have to add that number 5 times. So adding x1 5 times is nothing but multiplying x1 by 5, where 5 is the frequency of that particular value. Now similarly, your data point as x2, which is repeated 3 times. Say in that case, it will be x2 into 3, where 3 is indicated by the frequency. To obtain the sum, you have to add all these x1 along with x2. So you are doing f1 into x1 plus f2 into x2 plus f3 into x3, where your f is indicating how many values are there. So you have 5x1, 3x2, and certain number of cases. So your total frequency indicates the number of observations. If you have not understood what I am trying to say, you can have an example here. So I have certain data points, say 3, 2, 0, 1, 3, 4, 1, 2, 1, 0. Now if you look into the mean, it is just sigma x divided by n. So we have certain raw data observed here. So if you look into the sum, you have 9, 10, 12, 15, 23 divided by 12, 13. So the average comes to 1.7692. Now for the same data, if you look into the definition, or if you convert that into a frequency distribution, so you have x values which are 0, 1, 2, 3, 4. These are the 5 possible cases, of which 0 is repeated 2 times, 1 is repeated 3 times, 3 is repeated 3 times, 2 is repeated 3 times, 4 is repeated 1 time. Yeah. 1, 2, 13, 1 is repeated 4 times. So if you look into total frequency, your n, that is giving you the count. And if you look into the sum, now to compute x bar, you will do 1 plus 2 plus 3 plus 3 plus 2, etc. up to 1 and 0, which could be written as 0 plus 0 plus 1 plus 1 plus 1 plus 1, because we have 4 times 1, which is mathematically same as the product of f into x, 0 into 2. So this is 0, 1 into 4. So this is equal to 4. So you're doing 0 plus 4 plus then you have 2 repeated 3 times. So the sum will be 2 plus 2 plus 2, which is same as 2 into 3. We'll have 3 into 3, 9, 4 into 1, 4. And if you look into the count, sigma fx, so that is equal to 23. Therefore, your mean comes out to be the same 23 by 30 numerically, but the structure of the formula changes and we say it is fx because we have representing x also in terms of f. The total x is same as total of fx. Therefore, for discrete frequency distribution, we say the formula to compute mean is x bar is equal to sigma fx divided by sigma f. And you can take this as an example problem. So you have to keenly observe the data here, whether only x values are given, whether a frequency distribution is given, and then apply the suitable formula. And don't waste your time in the examination by converting the given raw data into frequency distribution, because this usually takes time. But since you have the calculator, though we said the number of observations will be very less, so just use the calculator, obtain the total, use this. So if we have given you a ready-made distribution with x and f, then in that case you can just use the formula x bar is equal to sigma fx divided by sigma f. And even for continuous distribution, we use the same formula, x bar is equal to sigma fx by sigma f, but we assume the values of x to be the midpoints. So you have class interval, compute the midpoints from the class interval where a particular midpoint is defined as the average of the class limit. So it will be lower limit plus upper limit divided by 2. So if you have the intervals like 0 to 20, 0 to 10 and 10 to 20, the midpoint in 0 to 10 is 5, from 10 to 20 is 15. So you can get the values of x, and we assume that these midpoints are actually the value of the variables, and it gives you the answer close to the actual x bar, because the assumption is always true because of the property of central tendency. What we say, if you have certain data, most of the data points will be close to the central number. So here I have grouped all the data which comes into 0 to 5. So if the property is really exhibiting the property of central tendency, then all these three values will be closer to 5. So that's why we say 5 is the midpoint, and that works in most of the cases. You can argue, what if my data points are all 1, 2, and 0? But as said, if you look into each and every case, that might happen. But when you look into the on a whole, you will have larger values, you will have closer values also. So maybe in that case, the small values are assumed to be 5. In such intervals, certain large values will be assumed by a smaller number. So it somewhat balances the entire case, and the formula works out. So even in this case, we say x bar is equal to sigma fx divided by sigma f. Okay, so I have to join back